For the third task, this is the third task that we're talking about. It's about cognitive biases that affect science. It's a relatively simple task compared to everything that you've done before. So for your RRR assessments and for your application extension, it's very empirical. So you have to do lots of stats, power analysis, R, Jamovi, read all these. This one is more like a review paper. It helps you to kind of gain an understanding of things that we talked about in terms of open science, but bridging this to things in social psychology and judgment decision-making. And I think this session is going to give you a bit of a taste, a teaser to some of the things that you will, that you could choose to do the review on. So the topic is cognitive biases in research. And today I will show you some cognitive biases in research in us, in the way that we do things. And I'm going to show you that even for me, and even for people who have been doing research for a very long time and started this whole thing, even they admit that they're biased in some way. And the question is, of course, how to overcome this bias, how we can use open science for that. So with the help of the teaching assistants, we have this template, which is basically another Google Doc that will make duplicates for you and then make it available for you. So Christy is going to help me by assigning these to you. We'll have some topics. You could actually choose which topic you want to do. So we'll have things like hindsight bias, outcome bias, confirmation bias, overconfidence, all sorts of things regarding biases in judgment decision-making. And then your task will be to review these biases and then see how this applies to research. So what is it in the research process, in the way that we do science, is applicable to that? It's pretty straightforward. It's also not that long. So I try to do this as simple as possible in just giving you guidelines what to do in each section. So you're kind of familiar with this. My general request here is that don't overthink this. This is not going to be, 500 pages. Split the work between you, try and replace these paragraphs with brief paragraphs. Just do this in a way that would allow anybody who is not taking this class or is not familiar with social psychology or judgment decision-making to understand what's going on in research and understand what's going on with this cognitive bias. So hopefully this is like a step-by-step on how to get this done. It's a slightly different task from last semesters. So we don't have very good examples for this template, but I do have examples from people who have done similar work. Actually, there's one person who has done similar work. Her name is Dorothy Bishop. And she's the person who started this whole domain. And her claim is simple, and I really like this claim. It's like, we're social psychologists, so we're studying people, and we're studying interactions, and we're studying the way that our mind works. But we assume things about people which we don't think applies to us. So we don't apply some of the implications and the things that we know from what we advise to others about how we should do things to protect what we do, which is very important, how we do research. So I'll give you a bunch of examples for that. So you can follow the link and we'll have some more details later this week. All right, so we'll start out by a few questions, kind of typical for us to start with a Mentimeter. So I'll ask you to kind of, you already have some familiarity with this design, so you're already experienced experimenters. So as you're answering this, my question to you is, what is this about? What are we doing here? And the task here is to rate yourself compared to the average HKU student. We've done something similar like this in morality and some other domains. And the categories are the following. So dependability, being able to be counted on or relied upon. Objectivity, how objective you are. Being objective, basing thoughts on actions and objective facts and truth. Consideration for others, how much caring for and about others you are compared to other HKU students, classmates. Snobbery, being a snob, thinking about oneself and acting as being better than others, deceptiveness, and selfishness. If you recall with morality, what it is that I had is like a different item, one for you, one for the other, one for you, one for the other. Here, I'm asking this in the same question. I'm just giving you, compare yourself to others. Much more than the classmate and much less than the classmate. So the midpoint is you being just like the classmate. And then asking you on different categories. What do you see with these categories? What do you see? What do you expect in this kind of thing? Yeah, higher on the positive one and lower on the negative one, right? What do we call this kind of design? What is this design? So comparison to others, there are 6 categories, yeah? So we can actually average the top 3, and we can average the bottom 3. So we have these 2 factors. They're not in random order, but each participant, which is you, does all of them. And this is what we typically call a within design, right? So if you only saw the positive or only saw the negative, this would be a between design, right? Good. So let's see if the predictions, this is of course you already know me very well and you know these designs, but still even here, your predictions seem to be supported. So relatively higher, we see like a nice distribution here. The most are in the middle and higher for the positive and lower on the negative. Another question. So here I have, instead of in one question, I'm separating this to my own self-serving tendency and then the average classmate self-serving tendency. And I'm explaining what psychologists have found. Psychologists have claimed that some people show a self-serving tendency in the way that they view their academic or job performance. That is, they tend to take credit for the success, but deny any responsibility for failure. They see their successes as the result of personal qualities, like drive or ability, but their failures as a result of external factors. So rating these on yourself and then rating this on the average classmate. So here the manipulation, it's still within design, but the manipulation is self versus others, right? And then we can compare these two. The next one is the halo effect. So also a comparison. Psychologists have claimed that some people show a halo effect in the way that they form impressions of attractive people. That is, when it comes to assessing how nice, interesting, sociable someone is, people tend to judge an attractive person more positively than he or she deserves. So here again, rating yourself versus rating the others. So what are your predictions here? Yeah, so people tend to perceive themselves as being more objective than others, less biased than others. Yeah. So if you look at the results over here, even in our very educated sample, we perceive ourselves to be lower and less biased than others. And also on this one. What am I trying to show you? What is this about? This whole thing is a phenomenon, and it's called the bias blind spot. Blind spot is that we really think that we see the world better than other people, more objective, and that we are less biased than others, but obviously, and it's very easy to show, we have this kind of bias. So even though in the first question, we show participants just how biased they are, so we actually give this to the participants, and then we say, see, this is exactly what psychologists are saying. You see yourself in a self-serving way. So we explain to them, this is very, very common. And then we ask them, how biased are you? So we show them the bias, we give them evidence that they're biased, and then we ask them, how biased are you? And people still say, we're less biased than others. So this is the bias blind spot. We still, even when confronted with evidence that we are biased, this is still a blind spot. We still don't see the bias in us. So this is a classic phenomenon. The first one that I showed you, the self-serving bias, is called the better than average effect. So last Friday, we had Cora Mock give the brown bag, and I think I posted the video on the Slack. So she did her thesis, a master's thesis with me. She was the first, she was a very brave soul, one of the first to do replications and extensions with me. And it's amazing because, as you can see, this was in Psychology Today, and it was later published in SPPS, which is a reputable journal. So she's done a very good job. And it's amazing because this is 1985, and we used exactly the same kind of items. And the effect size was like comparable, very, very similar results. So 35 years later, we were able to get support that people see themselves as better than average. But even when we show this to participants and we say, we found that people think of themselves to be better than others, even when they're not. And then we ask them, so how biased do you think you are? And people still say that they're not biased, which is a different one, which we also replicated. It's called the bias blind spot. So people find it much easier to notice bias in others, but it's very difficult for them to see the bias in themselves. So they think that self-biases are lower than other biases. So this is the summary of the British Psychological Society wrote about this. So Kit, who is going to be giving you some comments next week, and he's helping us with, he was the previous TA, he's going to help us from the outside. Now he's applying for PhDs. Did this, headed this sort of thing, and this is the headline: good news for science, bad news for humanity, the bias blind spot just replicated. So the whole team together, and this was finally published in Judgment and Decision Making. So very successful replications. What is the relationship between this and research? What is the relationship between this and science? How can we apply these two biases to how we evaluate, how we see, how we do research? What is the connection? So this is actually a very interesting case study. I love this. And it's called "A Physics Professor Bet Me $10,000 I'm Wrong." So there's this YouTuber that I follow. He has 10 million subscribers. He's one of the most successful YouTubers, and he communicates science. And he did this amazing video about how, without any energy, any battery, you can have a speeding car of sorts, just propelled at the beginning by the wind, but then it keeps accelerating, even not dependent on the wind. So he posted a YouTube video on this. And usually this YouTuber is very, very careful to show scientific evidence. And he got a lot of pushback, people telling him that this is not scientific evidence, what you're showing is not real. And the most amazing response came from a very well-known UCLA physics professor who told the YouTuber that he is wrong. And the question was, who do we believe? Do we believe the YouTuber, or do we believe the very reputable UCLA professor? So first of all, he's a professor. Second of all, this is Ivy League UCLA. So which one of those two would you bet your money on? I think a lot of people bet on the professor. So now we're going to see what is going on over here. I'll show you 3 minutes of what was happening. And I want you to notice the two characters. We're going to meet the YouTuber many times after. I'm going to show you some videos about how he shows cognitive biases. I want you to see his attitude, and I want you to see the UCLA professor's attitude. I want you to think about what is going on in their perspective. What are they thinking about the problem? How are they facing this issue? And which one of those seems to be better for science? Which one is the more scientific method?
I am here to sign a document betting $10,000 that my last video is in fact correct.
This is the video in question. Some people may have missed it, but in this car there is no motor, no batteries, no energy source besides the wind itself. And the counterintuitive claim is that this car can maintain speeds faster than the wind that's pushing it.
There is a physics professor at UCLA who got in touch to say that he thought that I was wrong, that the explanation was wrong. You know, we went back and forth a little bit, and eventually I said, well, how about we bet $10,000? I can prove it to you, this vehicle really can go downwind faster than the wind. And to my surprise, he is taking me up on the bet.
Look, no one is perfect. but you have a much lower error rate than most people on YouTube, in YouTube space.
Now, Professor Alex Kosenko wanted this wager and all related discourse to be public. In fact, he suggested we get a celebrity to witness the signing. So I asked Neil deGrasse Tyson, Bill Nye, and Sean Carroll to be our witnesses, and they graciously agreed.
And Alex, I just want to say, I agree with everything you said about Veritasium, that generally I can watch it and not have to wonder, is he going to mess up? How am I going to...
No, he's brilliant. No, he's brilliant.
I'm excited about this bet because if I am wrong, then I want to know. Like, the whole point of the channel is to get to the truth, and that is, I think, why we're all here today, and I think, you know, this is a great chance to sort of see.
I'm going to...
External examiners, do you know who these famous people are? You've never seen them before? Very famous professors and science communicators who try to explain science to people very famous on American TV.
To summarize Alex's main points in this video, but I'll put his full presentation here.
So let me first explain what I see in the video. In the video, the vehicle is operated in a gusty wind. Initially, you have the wind speed exceeding the car speed, but then the wind speed is not constant. The wind speed drops, and the car moves by inertia with deceleration for a while.
So basically, Alex thinks a gust pushes the car to a high speed, and then when the wind dies, the car is going faster than the wind momentarily, but it must be slowing down.
In fact, that will be my conclusion at the end of this presentation, that whenever you have velocity faster than the wind, I'll actually show you in an equation, the acceleration is negative. Okay? The second effect is that the wind in the video is measured at the height of about a meter or meter and a half, but the propeller goes to some 3 meters above the ground.
Now, due to interactions with the ground, there is a wind gradient. Wind travels slower, close to the ground, and then faster higher up. Now, Alex estimated that the wind speed at the propeller might be 10 or 15% higher than at the telltale. So it's possible that the car could be moving slower than the wind at the propeller, and yet appear to be moving faster than the wind at the height of the telltale.
Okay, I'm gonna stop here because this is not a physics lecture, and maybe you missed some details because you haven't watched the original video. But I want to get like your first impressions on, even if you don't understand exactly what's happening with this car, what do you observe? What is it that you see between these two characters and how they decided to resolve this? Yeah, the professor wants to give feedback and they want to get to the truth. The way that they're doing this so far in this video, like what is the UCLA professor doing? Equations, right? So what happened is that the YouTuber showed a video of this working, right? And then the UCLA professor said, this cannot be because equations. Let me explain to you with equations why what you showed is not real. This debate is not very helpful, right? What is the problem with this kind of debate? The YouTuber ran this and did this already, and now the UCLA professor is convincing him that what he actually did cannot be true because he has equations. Now, what is a better way to actually resolve this kind of situation? So they put $10,000 on the line from their own money to bet. What can alternatively you can do with this $10,000? Just what? Or try it out. The UCLA professor did not even think about trying this out. He was just willing to bet $10,000 here before trying it out himself. Many times, you know, we do replications and extensions of stuff that's never been replicated before. Why? Because somebody, you know, ran this and we take it for granted that this works or not. Even if you show, let's say we run a replication and it's a failed replication, people are saying, can't be that this is a failed replication because equations, because this has already been published, because, you know, this is in a journal, because the professor is from UCLA, because of all these things. But the way to resolve things like that usually, just repeat this again and see if this works or not. If it doesn't work, then we can try and learn from that. So I'm going to show you the approach by the YouTuber. So rather than, so he was a little bit worried about this, you know, equations, what am I going to do? Maybe what I did was not real. Let's just try and do this again and again and see whether I can get to prove just by evidence of replication that this is actually working out. This is, by the way, the response by the UCLA professor, just like back and forth on Twitter, YouTube. I disagree. How shall we proceed? Am I expected to produce a critique of a critique of a critique? So every time the YouTuber says, but here's the evidence, just try this. And he says, no, but can't be because equations. And he says, no, but here's the evidence. And he says, I don't want to keep giving critiques. So maybe we should move this to like academic articles where we can discuss more equations in peer-reviewed journals. So the biases that I observe here with a UCLA professor who's supposed to be all about evidence and science is, first of all, authority bias. I am a big researcher. You're a YouTuber. I know because I've spent my entire career working on this. So it can't be that some YouTuber just comes over and proves something to me. And this really affects open-mindedness and illusion of knowing. This again goes to the bias blind spot. I didn't show you the whole video, but he just assumes that the only thing that's creating this phenomenon is because subconsciously, the YouTuber and whoever is running the experience is biased. So they don't know that they are biased. Therefore, they're creating this even though it doesn't exist. So he's assuming bias in others, but he completely is ignorant to the fact that he might be biased and not willing to be confronted by evidence. The equations thing, so theorizing rather than testing, just run a replication. Just try this yourself. $10,000 US, you could have used half of that in order to construct this. And I'm going to show you how the YouTuber did this with $30 US. You don't even need $10,000 US. And then he says all kinds of things like, I'm 100% sure. Especially you're a physics professor, string theory, quantum mechanics. What is this in this world that we're 100% sure of? So whenever I have a scientist that says, I'm 100% sure that my stuff is going to replicate because I've replicated this many, many times, and I get this kind of responses. I reach out to original authors and I said, students at HKU are going to run a replication. Can you help out? Can you give us some insight? He's like, there's no need to replicate this because this is 100% sure that this is going to work out. I've seen this many times. So you can think about your own things here. I'm going to show you the lessons learned from this and then a proof on how this works.
Thank you, Neil. Thank you very much.
Guys. Thanks, Neil.
Guys.
So now it was up to me to convince Professor Kosenko that Blackbird really can go faster than the wind. But his presentation was effective. When I posted about it on Twitter, Alice Zhang, who runs Chinese Veritasium, said, I think you lost, Derek. I'm 80% on Alex's side now. What's amazing to me is that neither one of them had seen my attempts to replicate the treadmill experiments. For the first video, I asked my friend and YouTube maker Zyla Foxland to make a model downwind cart.
Oh no!
Version 1 ended in failure, but Zyla was undeterred, coming back in a couple days with version 2.
Is it feeling like it's gonna...
Unlike these models, most of her projects actually work. She is determined. So maybe this tells us something about whether you can actually go faster than the wind downwind. What was clear to me is that I didn't do a good enough job in the first video explaining how Blackbird works and providing convincing evidence that it can really go faster than the wind in a sustained way. In my defense, I thought the concept was well enough established. Way back in 1969, Andrew Bauer built the first successful downwind cart.
So lots of fascinating things. I'm not going to go into this. You're welcome to look at the video. But the YouTuber did his research, the historical aspects of this machine without the equations and without, all the physics. He just went and saw what the evidence was, and he looked at the relevant literature. And this is how he communicated things. Based on what I've seen, I think that this works, and here is a demonstration. Now, one of the takeaways, and I really like this sort of humility, is that he's saying, what can I learn from this? What have I done wrong that I was not able to convince a UCLA professor? And I think it's really good that he is contemplating, perhaps I didn't share enough materials, perhaps I didn't share all my evidence, perhaps I didn't explain the historical background. So in many of the papers that you're trying to replicate, there's lots of materials that are missing. Perhaps, the professors think that their stuff is going to replicate. They're very sure, but they have some evidence that they haven't shared with us. We're trying to reproduce and build things from the beginning, but it's very, very difficult because we don't have access, not to their data and not to their materials. Today, we got a few materials, with some faces that we're going to use in one of the studies. I was very concerned about whether these faces, the faces that we're going to use are going to be close to the faces that they used, by the comparison between the average American and an Asian American. But now that we have actually the authors replied and they were very positive, and now they gave us their actual materials, so we can repeat this again and see if this really works or not. So the YouTubers actually has some self-reflection on what is it that he can do, and it all boils down to one thing, and that is open science, transparency, sharing as much as possible, and communicating things a little bit better. So in order to overcome these kind of biases, so one thing that they did is really nice, external trustworthy judges and making everything public, and all sorts of other measures that they had in place, like big figures who understand science to come in and observe the situation. Open science is providing a full explanations with no assumptions whatsoever from the beginning to the end, with no gaps whatsoever. And then ensuring that all the evidence is checked and evaluated, and then doing reproducibility and replicability, not just by himself, but as you'll see here, he has also shared everything that he does and invited others to conduct their own replications of what it is that he did. So I'll show you the proof.
Does it work?
It totally works.
Amazing.
Oh my God, it's so good.
Her fourth version of the cart works spectacularly, and it was designed to be replicated by anyone using just a 3D printer and a simple list of materials. She explains how to build it with more details on the engineering process on a video over on her channel, so go check it out. Now, Professor Kosenko has now conceded the bet, and he transferred $10,000 to me. So I want to thank.
So that is amazing. A YouTuber versus a UCLA professor who's supposed to be an authority in physics and whether this is possible or not. How humbling this experience is. And how did he do this? Open science and replications. Now, anybody with a 3D printer can take this, do exactly the same thing, and see that this works. Before, you can have a debate because it wasn't so clear, not everything was shared, and then maybe some people can debate. Now he has given conclusive evidence, and the way to do conclusive evidence, share everything and replicate. Any thoughts on this? Even professors from UCLA can be very, very biased. Some students are worried when they talk to me on Slack and they think maybe I know a lot more than they do. And then like every word that comes out of my mouth or everything that I type, they consider this to be the whole truth, nothing but the truth, high quality. Sometimes I don't know what I'm doing, and I'm always ready to reevaluate where I stand and what the evidence is. As long as you tell me what it is that you're doing, as long as you explain this to me. It happened a few times on Slack that students wrote something, and then I replied and they say, "No, professor, this is not exactly." And then I'm like, "Yes, you're right. Thank you so much for helping me understand this better." And right now, you're the experts on your articles. You know this much better than I do. So if you see something that I might be wrong, this is how we have a conversation, we have a discussion, and then together we get to the truth. The way that you will explain and share the evidence with other people is through open science. So in your replication and extension projects, be as transparent and as clear as possible. The reason why we're doing what we're doing, the reason that we're doing this as a registered report, is that we're trying to de-bias everything and allow everybody else to look at the evidence without, objectively and without any other biases. So I consider this is from this year. So you can see this is July 2021. So this just happened. And when I saw this and how this blew up on Twitter, Facebook, YouTube, I thought this is just like a fascinating case study of how much we in academia have to learn from YouTubers, from students, from the entire community, the public. So we really need a lot more engagement. So I'm very grateful for people like this YouTuber on how well they're doing at communicating and testing science. They're holding us accountable for the things that we communicate. They're making us revisit some of our assumptions. So I think that's extraordinary. Some of the slides that I'm gonna use in order to show you some cognitive biases are from these resources. So I have Dorothy Bishop, we'll meet her a little bit later. She is the one who started this whole domain. At the beginning, I didn't know that this thing exists. I studied judgment decision-making, and I was very worried about researchers having a lot of cognitive biases, but I didn't have any evidence for this. I was planning to do things on my own. And then Dorothy Bishop came out with a few things that I'll show you. And her work actually came to change policy because she's a very, very well-known researcher from UCL. Unfortunately, this year she retired. So you are the next generation of Dorothy Bishop. It's up to us together to do this kind of thing. And the reason why we're doing part 3 and we're doing this kind of assignment is in order to build on her work and show how cognitive biases actually happen in science. So we're taking the foundations that she built to a next level. One example for policy is the DORA assessment. So for example, in order to get the job at HKU and in order to get grants and promotion and anything else at HKU, I need to meet an assessment criteria. I have a review coming up in a couple of weeks where I'm being assessed. How are researchers assessed at HKU? Do you know, how do they determine whether I need to get a bonus or whether I should be promoted? What is the number one factor? Nobody's reviewing my work. They're not looking into my work. How do they establish whether I'm doing good enough research for HKU? How many articles I can publish? This is a very, very important factor. What's the second factor related to this? Which journals? We need a high impact factor. So we want to aim for Science and Nature and PNAS and all these big journals. So you don't actually look at the articles. Nobody's going to read my articles for my review, but they are going to look at my CV and see the number of publications and see where it was published and look at their impact factors. By the way, I don't know if you are aware of how impact factors work, but impact factors are the number of citations that a journal receives divided by the number of articles that the journal has published in the last 2 years. This is what an impact factor is. The problem is that even if you publish in such a journal, nobody is saying that you're going to be cited like this. The only thing that it says is like, on average, the whole journal has been cited a number of times in the last 2 years. There's so many things that are wrong with impact factor, but the way that we are being evaluated is by impact factor and by number of publications. This is very wrong, and DORA is a world movement based on some research by the open science movement and people like Dorothy Bishop that are showing that this is very biased and this is not how you establish quality and integrity. Therefore, DORA is working to change, and a lot of universities have signed this, mostly in the UK, Western Europe, Netherlands, some in Australia. Somehow the US is kind of lagging behind on this. Hong Kong is really lagging behind on this. But the good thing is that Hong Kong, at least 2 years ago, hosted the World Conference for Research Integrity, and they have signed the Hong Kong Principles of Open Science. So hopefully HKU will get there. But many of the slides that I took are actually from DORA, trying to show that people in research have all these biases, and in order to overcome these biases, we need to assess them differently. So if we assess people on impact factors, a number of publications, they're going to do very well on this, even if the integrity and the quality of science goes down. I'll show you some examples from Dorothy Bishop, Dora, and other people who are involved in researching cognitive biases. Tversky-Kahneman. Kahneman won the Nobel Prize. Tversky, if he would have been alive, he would have received this together with Kahneman. And in the 1960s and the 1970s, what it is that they've done is document cognitive biases in people overall, but they also went to statistician conferences and researchers and showed that even researchers have these kinds of biases. They made the differentiation between effortful, deliberative thought to intuitive and effortless thinking. And I'm going to show you some examples about how sometimes we misplace, base things on our intuition rather than doing the more effortful thing. So we have all kinds of processing. We have processing that is based on our experience. And obviously our experience is a sample size of 1, so it's a little bit biased. Based on experience, we do things based on what has worked before. So if something worked for us, we're just going to keep doing it again and again. It gives us some approximation of what is right. And the good thing about this is that sometimes it saves us a lot of time by not having to rethink every time that we face this kind of situation. Heuristics, which is what Kahneman and Tversky started to map out, is this cognitive optimization that replaces a difficult but correct question with a much easier but incorrect one, which you can answer. And we're going to do a few examples together. And I think it's fascinating because these are really classics that started the whole domain of judgment and decision making. And of course, you've got the deliberative rational mode, which is a lot more slow and careful processing. So I'm going to ask you to kind of go along with me and answer some quick questions. I think some of you perhaps know this question. Assuming that we had 23 people in this class, so let's take any 23 people at random. What is the probability that in a class of 23, you have at least 2 people that have the same birthday on the same date? So give your estimation of what is the percentage, what is the likelihood of this happening, of 2 people having the same birthday in a class of 23 people. Are you calculating? Oh, can you share with me how you're calculating? No, even experts take a very long time. Even statisticians take a very long time with this. I'm going to show you some results on this when we ask statisticians and professors from UCLA what they think about this. Good. But you have some intuition, something comes to mind immediately. How do we do this intuitively? What do we rely on? What is the easier question to answer? We can't solve the difficult one. What is the easier one to solve? Yeah, guess how? What do we rely on? Yeah, in experience. So what is your experience in most of the classrooms with 23 people? Yeah, very, very small number, right? Yeah. So what would you estimate here? Yeah, we already know that there's like a game here. So maybe our intuitive reaction is not, but our intuition really tells us that this is very unlikely, right? Yeah. Any other guesses? Do you have a guess on like what is the percentage? So you replaced the difficult question with what's the easier question to answer? Randomness, coin toss, 50-50, that kind of thing. Okay, that's another heuristic in a way to look at this. So one is experience and one is more of like, let's replace this with something else. How about this other one, this next one? Let's say that you have a newspaper, these things that we don't use anymore when we use our mobile, but newspaper, which is 1 centimeter thick. How about you fold the newspaper again and again and again and again? How many times do you need to fold the newspaper until you get to a thickness that will arrive at the moon? How many times do you need to fold the newspaper? So if we look at some of your answers, we have slightly more than 40, like 150, 100, 700, 1,000, not something a person can finish in their lifetime. Or 20, who said 20? Why 20? Did you calculate?
I remember that.
Your memory? Okay, yeah. So these are interesting questions because actually they're very practical. Like you want to know what happens if you fold a newspaper. Do you want to know the answers to that? So when you look at this question of 23 persons at random, the intuitive heuristic response is, do I know people who have the same birthday, their birthday on the same day in this classroom or in classrooms? So very similar to what you did. So very intuitive heuristic. The experienced one is either, I faced similar questions before and therefore I know that it's a coin toss or 50-50, or you can say, my experience tells me that this professor is trying to trick me. Therefore, I will not rely on my intuition. I will do something differently. Or in your case, I remember something from somewhere where I saw something similar. Therefore, I'm going to take that and put it over there. The other thing that you can do, but that is very, very difficult. Like you say, you need to be like more of an expert to be able to calculate this, is the rational one. Simply calculate and solve this. So if you can't, then just contact other experts who can do this. So the answer is 50%. So coin toss was very close to this, but it's actually a 50% chance of finding. How is this possible? Now, there's a whole explanation here on how to do this. It's actually not very difficult math, but you need to know how to do this math. So the likelihood of no matching birthdays is 364 out of 365. So that's like 99%. And then the number of comparisons. So usually when you think about your own experience, you think, I've never had the same kind of birthday with anybody else in my class. But aside from you in the class, there's 22 other people in the class, and they have relationships with everybody else. So you need to think of all the comparisons, 22, 21, 20, and so forth. So you look at all the number of comparisons, and then this is by the power of that. So the likelihood of no matching birthday is 49.952. And then in order to have matching birthdays, 100% minus that, which is a little bit above 50%. Now you can look at this graph from Wikipedia. It's called the birthday problem. It's like the higher number of people, it goes up like that. And around 50, somewhere 50, 55, it gets to almost 100% of probability that this is going to happen. So the thing is that we think, okay, 23, not a lot of people, the chance is very, very low, almost zero. However, actually in reality, the chance is like 50%. So intuitively, we expect a very small probability, but the probability is actually quite higher than that. And a lot of things that people consider to be miracles or unlikely magical events are actually not. They're just like a lot more probable statistically than we expect them to be. We think, this is not ever going to happen. But we just have a very biased understanding of statistics. How about this one? Saturday's edition newspaper. So the experience response is doubling, multiplication, exponential growth. Be careful, take your time, calculate this. But the heuristic response is, let's replace this question with a much easier question of what's the distance to the moon? It's very, very far. Then folding takes forever. But then as we have some experience in this, and the only thing that you need is 35 times. Do you need a lifetime in order to fold 35 times? Why is this? Because we're very, very bad at assessing exponential growth. This is also one of the problems with a pandemic. If you have a pandemic where every person can infect 2 other people, the pandemic can get out of control very, very fast by everybody dying within, in no time. So this is actually for 0.1. I took this from YouTube. So you can look at this, but just look at what is exponential growth. It starts kind of like slow. So at the beginning, you fold 1 time, 2 times, you get to a fingernail after 3 folding. At 7, you get to the thickness of a notebook. At 10, you get to a width of a hand. At 12, you get to the height of a stool. At 14, you get to the average person. But here, because of exponential growth, it gets very, very, very fast growth. And very, very fast, you get to, even after 50 folding, you get to the distance of the sun. But we don't really grasp exponential growth very well because we don't have a lot of instances where in our lives we've seen and experienced exponential growth. I'm going to show you, this example is from a very famous Chinese historical tale about the emperor or the king and the beggar. And I really like this because this classic story, it's from one of the classic Chinese books. I can't remember which one, but this is the story. The king played chess against a Chinese chess, against the beggar, and offers a small fortune for a win. The beggar declines and asks instead for a different paradigm. So he tells the king, instead of giving me a small fortune, how about you will double the amount of rice for each square on the chessboard. So we start with 1 grain for the first square, double that for the second square, double that for the third square, and so on. The advisor for the king back then didn't have the way to calculate this, no mobiles and no way to look at this. So it tries to calculate and fails, and then the king contemplates and accepts. King lost the game. What does the king owe the beggar? What is the answer here? What's your estimation? If for every square on the chessboard, we have 64 squares, how much grain, how much rice does the king need to give the beggar? Are you calculating? So the intuitive heuristic, the easier one, is that there's only 64 squares. So no big deal, right? Like how large can this be? And we're only talking about a grain of rice, so it's this small. So probably, I don't know, like a sack of rice, maybe like the beggar really doesn't know anything. So he just lost a small fortune to get a bag of rice. But the intuitive experience response is doubling goes extremely fast. Exponential growth is really, really fast. Therefore, be very, very careful, as the emperor and the king, when you play chess with beggars, just be careful how you approach this. Take your time. So if we look at this chessboard, we see 1, 2, 4, and then it doubles all the time. After 64 of those, 2 by the power of 64 minus 1, this is the number. There is no amount of such rice in the universe as we know it. So there's no way for the king to pay this kind of debt. So the king goes bankrupt and the beggar becomes a very wealthy person. But the amazing thing is that most people, including scientists, find this very difficult to calculate or believe. Like how can this be? It's just a chessboard with 64 squares and it's just a tiny grain of rice. So that's like an interesting demonstration of this problem with exponential growth. So the lessons that we can learn from this is that people are very, very bad at estimating probabilities. They're very bad at numbers of different events, like the distance to the moon or the number of grain rice. So the solution is when problems are difficult, the intuition fails us if it's based on heuristic. So if you're a UCLA professor, even if you have physics and all this, and the YouTuber is showing you something, your intuitive response is, this cannot be, I am much smarter. Perhaps take the longer route, invest the $10,000 in order to just maybe try and check this out. So be very, very careful when you replace one question with something that seems to be an easier question, but it's not related to the other question. So the UCLA professor had his equation, but the equations had nothing to do with what the YouTuber was actually trying to do. Some of the later demonstrations that I will show you came from this lovely book, The Improbability Principle, Why Coincidences, Miracles and Rare Events Happen Every Day. So we think that they are rare, we think that these are miracles, we think that these are coincidences, but actually we don't understand statistics, so these are much more probable than we think. And then of course, thinking fast and slow. So we'll take a 10-minute break and then we'll come back and I'll continue to introduce you to Dorothy. So we have these two modes. One is the effortful kind of, and one is the more, it's a simplified version of our mind, but we do tend to avoid the effortful, deliberate stuff. And we do tend to go with our intuitions. And I'm gonna show you some examples for this. Our favorite YouTuber is going to demonstrate some of this, and he does an amazing job just going onto the street and talking to people and trying to test some of these cognitive biases. This is kind of like what we're trying to do here in this classroom, but I think after a while, you're kind of like picking up on what it is that I'm doing. So not everything works, but I think it's really fun to see how he does this in reality with people in the street.
For most of us, thinking is at least somewhat unpleasant. We try to avoid it where possible. For example, I asked these guys, how long does it take for the Earth to go around the sun?
How long does it take for the Earth to go around the sun? Do you have an intuitive answer? What did these folks say?
I reckon, cuz.
Is it 24 hours?
Obviously a day, yes.
It's obviously a day. Is it? For the Earth to go around the sun. Obviously a day, right? 24 hours.
Or take this problem, which has been given to thousands of college students.
You go into a toy store, and there's a toy bat and a toy ball. Together they cost $1.10. And the bat costs $1 more than the ball. How much does
the ball cost? There's an intuitive answer, but it's usually the wrong one. So this is what happens here.
the ball cost?
10 cents. We're all wrong, aren't we?
If you think about it for just a second, it's obvious that the ball can't cost 10 cents. Because if it did, then the bat would cost $1.10 and the two items together would cost $1.20. The correct answer is 5 cents. Now the point of these questions is not that they're difficult. Any of these people could have quickly checked their answer if they wanted to. The point is that they don't check. Because thinking is uncomfortable. It takes effort.
Hey, the Earth doesn't take one day to get around the sun. It takes like a year.
Now I think it would be easy to put these mistakes down to stupidity and believe that you, being much smarter, could never fall into such traps. But then I think you'd be fooling yourself. I think these examples reveal blind spots in all of our thinking due to the fundamental way that our brains work. Now one way of modeling how the brain operates is as though there are two systems at work.
Yeah, we're not going to go into system 1 and system 2, but I think you understand the kind of very intuitive answers and how they can fool us sometimes. All right, so let's consider this one. And this one has direct implications for your research and what you're doing, both in this replication extension and other things. Which hospital recorded more days with 60% boys? So in a certain town, there are 2 hospitals. In the larger hospital, about 45 babies are born each day. In the smaller hospital, about 15 babies are born each day. As you know, about 50% of all babies are boys. However, the exact percentage varies from one day to another. Sometimes it may be higher, sometimes lower. For a period of 1 year, each hospital recorded the days on which more than 60% of the babies were born. Which hospital do you think recorded more such days? So the average is 50%, and we're trying to record how many days had more than 60%, which is a deviation from 50%. Is it more likely in the big hospital or in the small hospital? In the one that has 15 babies or the one that has 45 babies? And the options are larger hospital, about the same, or smaller hospital. How to approach this? What's the right way to approach this? So usually when we have larger samples, the confidence intervals are wider or narrower. Narrower, which means that the error is much smaller, right? So the likelihood of you to fall far away is much less likely. So if you have larger samples, you're going to be much closer to the actual effect. If you have a small sample size, like in most of the originals that we're trying to replicate, it's going to go all over the place, up and down and up and down, which is very similar to this question. But a lot of researchers get this wrong. So they don't really think about power. They don't think about sample size. They don't think about this kind of thing. So a lot of people here answer about the same. Why do we care if it's 45 or it's 15? It's about the same because, 50%, 60%. But actually power or the sample size really matters. So this is from Dorothy Bishop. This is her slides. So this is the problem that she cited from Kahneman and Tversky. And this they've shown to statisticians and scientists. And statisticians and scientists got this wrong. How to demonstrate this? This is the distribution of the hospital that has 15. So 50% is the actual rate in the population between boys and girls. But you can see the red one is much more, the error goes up and down. So the distribution is much wider. But the hospital with the 45, it's much closer. And if it deviates, it doesn't deviate by a lot. So it's a lot more likely that you'll get more than 60% in the smaller hospital. So smaller sample gives noisier estimates. So it could be, that the original that we are replicating found an effect, but it could be just because of random noise. They detected something. We're not doubting, their integrity. We're saying maybe they've really observed something, but with such small samples, much more likely of them to detect something even if it's not actually there. right? So this is what's called the belief in the law of small numbers. It's a classic paper. It was the foundation for the Nobel Prize winning research. People have strong intuitions about random sampling. These intuitions are wrong in fundamental respects. These intuitions are shared by naive subjects and by trained scientists. So even when giving this to trained scientists, a lot of people get this wrong. I'm going to skip this one, but I'm going to show you this kind of this distribution. Let's say that you decided to run a study with 2 groups of n rats. What value of n should you start with? Let's say 20 per group. Here's a sample of data. Do you think, based on this plot, that there's a difference between the experimental and the control? So you look at this data, and you're saying, okay, I have 20 per group. It looks like in the plot there's a difference because this one is lower than 0, this one is higher than 0. But because this is a very small sample, actually it could very well be that they're coming and there's actually no effect. So these 2 samples are just by random noise drawn from the same kind of sample. However, it could be that we're observing something that has absolutely no evidence for an effect. Both of them are very similar to one another, but because the sample is very, very small, it could be that they're coming from a different distribution. And one of the fundamental things that most people don't understand about effect sizes, especially Cohen's d, when you compare an experimental and a control, is that actually, when we think about differences, we tend to think about differences in the way that's on the right over here. How most people think about group differences. If there's a Cohen d of 0.5, then it means that this distribution is very different from this distribution. But actually, the distribution, the differences is in the mean, but the distribution, there's a lot of overlap between these 2. So this is the reality, not this one, but what we think is the reality is the one on the right. How to demonstrate this? So when an effect size of Cohen's d of 0.2, you can see some differentiation as the sample size increases. So sample size of 20, it's very, very mixed. You can't really differentiate between one group and another group. It gets a little bit better when you have a sample of 40, sample of 60, sample of 80. But the higher that you go, then you can see the differentiation. If the effect size grows, then you really see a differentiation. At the beginning, it's a little bit difficult, but then the higher you go, the easier it is to understand. So this is the DORA summary principle. One last slide. I know these are a little bit frustrating, and this is going to be the most frustrating of all of these, but there's something very, very important for me to demonstrate here for you. So make some effort, even if you don't tell me what your answer is, to solve this. This is a classic demonstration of cognitive biases in researchers. So here's the question. Each card has a number on one side and a patch of color on the other. You are asked to test the hypothesis that for these 4 cards, if there's an even number on one side, then the opposite side is red. Now you want to test this hypothesis with a minimum number of cards. Which cards should you turn over to test this hypothesis? Which are the most important cards that you want to flip over here in order to test whether if you have if you have an even number on one side, then the opposite side is red. People see even and they see red. So they say, let's flip the even and let's flip the red. Then we'll know. Okay. So if we flip this red and we see an even one on the other side, then we find support for our hypothesis. If we have this even one here and we flip it and it has red, then we found support for our hypothesis. But that's actually not the case. Why? I'll show you a video with our favorite YouTuber. And after you watch the video, you tell me which card you need to switch.
I'm going to give you guys 3 numbers, a 3-number sequence, and I have a rule in mind that these 3 numbers obey. And I want you to try to figure out what that rule is. But the way that you can get information is by proposing your own set of 3 numbers, to which I will say, yes, that follows my rule, or no, it doesn't follow my rule, and then you can propose what you think the rule is. Is that fair?
Yeah.
Yeah, okay, so here are the 3 numbers. 2, 4, 8.
2, 4, 8.
You don't need to continue the sequence. You can propose a totally different sequence, whatever you want to propose, and I will simply say yes or no. That follows my rule.
2, 4, 8. 16, 32.
16, 32, and
64.
Those also follow my rule.
Okay.
What's the rule? What do you think?
Multiply by 2.
That is not my rule.
What?
That's not my rule. But you're allowed, if you want, propose 3 other numbers.
3, 6, 12.
3, 6, 12.
3, 6, 12 follows my rule.
10, 20, 40.
10, 20, 40.
That follows the rule.
Yeah, I'm still multiplying by 2.
I know.
Oh.
I know what you're doing. And yes, it follows my rule, but no, it's not my rule.
5, 10.
10 and 20.
Follows my rule.
100.
200. 400.
Follows my rule.
500, 1,000, 2,000.
Follows my rule.
Want me to keep going?
But do I just keep going? You're going to tell me your rule?
Am I doing it the wrong way? Am I approaching this the wrong way?
You're totally fine,
okay.
But you're approaching it the way most people approach it. Like, think strategically about this. You want information.
Yeah.
I have information. The point of the 3 numbers, right, is to allow you to figure out what the rule is.
Yeah.
Okay, I'm going to give you the numbers that I don't think fits the sequence and then see what you say. So I'll say 2, 4, 7.
Fits my rule.
So whatever I propose is right?
So is your rule like you can propose any number?
So the rule is anything we say is yes.
No.
Damn it.
But you are on the right track now. Hit me with 3 numbers.
3, 6, 9.
Follows my rule.
Oh, that didn't follow my rule.
This is good, right?
5, 10, 15.
That follows my rule.
What? Oh. Really?
Yeah.
I don't believe this.
1, 2, 3.
1, 2, 3.
Follows the rule.
What about 7, 8, 9?
Follows. Yes, that follows the rule.
8, 16, 39.
Fits the rule.
Excellent.
But we're no closer to the rule. I want you to get to the rule. How about 1, 7, 13? Follows the rule.
What?
11, 12, 13.
How does this
follows
make
the rule.
sense?
10,
I don't
9,
know how
8.
to do this.
Does not follow the rule. 10, 9, 8 does not.
Oh, so is it all in ascending order?
Booyah.
Okay.
Up top. Yes, first
that
ones
what it
to get
is?
it. You guys nailed it. That's the rule. That's the
always-
rule. Increase numbers in increasing order.
This is amazing. All she needed is one counter example. And based on that, immediately she knew what the rule is, right? What happened up to that point? They were stuck on something. They were following the pattern of just trying to find support for a hypothesis, rather than trying to reject, right? Find something that doesn't fit, something that is an outlier over here. So fascinating demonstration of confirmation bias and how we try to find supporting evidence, but actually what we should be looking for is finding evidence that would reject. So in this kind of thing, usually people go for B and C, but that actually does not tell us, as much as D, which is critical because it has the potential to disconfirm the hypothesis, but this one is usually overlooked. So if you turn this and it has an even number, then you know that there's a problem, right? You can come back to this. So this was used by Mahoney in 1976. So he went around and gave this to scientists, to academics, in psychology departments, and asked them, can you tell me what's the right way to do this? And he only found that 10% correctly identified the critical cards. So the way that even if we do a null hypothesis significance testing and we use p-value and we do all sorts of things in a psychology department, we also fall into these traps because our mind gets stuck on a certain pattern and we keep repeating that pattern. Even if we don't have a good understanding of that. And I want to show you that even Dorothy Bishop, who started this whole thing about looking at cognitive biases in researchers, fell into this trap herself. And this is where she contemplates and she shares from her own experience how she fell into this trap of confirmation bias.
I want to move on now to say something about confirmation bias, which you'll see how this comes into the position. It's another sort of cognitive characteristic of people, but if you put it together with p-hacking, you get into really serious trouble. But let's look at confirmation bias on its own first. So it's basically, it can operate at various points in the research cycle. I'm going to focus on an aspect of research that isn't much focused on, which is how we select other work to cite when we write our introductions to papers, for instance. And I think virtually everybody in this room who's ever written a paper will be in the position of knowing very well that what you do, typically, is exactly what is described in this wonderful little cartoon. You sort of think, well, there's two sides to this question. I'm going to really try and find some evidence. And you go onto Google and you go, Google, or you might, if you're a scientist, go onto Science Citation Index, but you go, blah, 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 and then you find a paper that says exactly what you want to hear, and you go, jackpot, you don't look any further. There you are, you've got what you want to cite. And again, we ought to probably feel bad about this because it's a very biasing sort of thing to do, but it's very much how we're wired up to think and not to go around. In fact, we would suffer from terrible information overload if we processed everything that's out there. So we're very much people who we're certainly not behaving like Popper would like us to behave, trying continually to disprove our hypotheses and our beliefs. Life would get very, very tiring if we did that. Instead, we tend to be looking for supportive evidence. Now, I want to sort of use myself as an example because, you know, it's very easy to point the finger at other people, but I think that because I'm saying these things are generally human things, I think I want to illustrate that even with the best will in the world, one does this. So here's a personal example of suppressed memory for relevant research when it doesn't fit. So one of the things I work on is children's language disorders, developmental language disorders. I'm very interested in genetic factors. So I've done twin studies on this, and I've given lectures on the genetic basis of developmental language disorders, where the main interest is in comparing in monozygotic, I don't know if I can get this thingy to work, no, never mind. The column saying MZ is the agreement between two members of a twin pair if they're monozygotic twins, as opposed to dizygotic twins. And the prediction from a genetic model is that identical monozygotic twins will be more similar to each other than dizygotic twins who have only 50% of their segregating genes in common. And here we have 3 studies, 2 from the States, 1 British one I did, coming to pretty similar conclusions, all quite small sample sizes, but these are hard kids to recruit, but pointing to really to quite a strong genetic influence on developmental language disorders. So I would go around giving this lecture saying, look, we've got all this evidence it's a highly genetic condition, highly heritable. And then this study came along in 2005, and it looks completely different. So there's not really much evidence, well, there's no evidence for any genetic effect here, and indeed the agreement between 2 members of a twin pair is quite low. And I had found, you know, I suddenly realized that although I had known about that study, when I was preparing talks and things, I just never thought to put it in. I sort of managed to mentally suppress its existence. And it was only when I had to do some more systematic review that I sort of came up against it again and thought, oh yeah, that's that study by my PhD student. She wasn't at the time working with me, I have to say. She had moved on to work with Robert Plomin, where she did this study, but nevertheless, I knew her.
So she does a certain kind of study where she compares different types of twins in order to look at genetic factors. And she was citing this kind of evidence to show, for her talks, there is some differences, look at my data. And she is here, this is Bishop, Dorothy Bishop over here, and she looked at 2 other studies that show differences, but then she completely forgot the existence of one other study that actually shows absolutely no differences between those. This is this one over here. And the amazing thing about this is that how can she forget? Because this is a study that was done by her PhD student. So even somebody who studies cognitive biases in researchers and knows about confirmation bias and tries to address every possible aspect of being very, very objective, falls into the trap of completely forgetting about something that counters her own evidence and what it is that she's trying to do in the talks, which is quite remarkable. And I like it that she shares from her own experience. And many times I also share from my own experience of, before I knew anything about open science, how I did research and how that was kind of backfired and is counterproductive. How did she address this? How did she find out that she has this kind of problem? She did what is called a systematic review, a meta-analysis, where she tried to combine everything. And a systematic review really forces you to look at all of the evidence one by one, and you can't really skip and overlook anything because you have keywords and everything needs to come up. So really fascinating example. So I just want to show you the end of this YouTuber.
Numbers in ascending order. 1, 2, 3, 4, 5, 6, 10, 15, 25, doesn't matter. Any numbers in ascending order. I was inspired to make this video by the book The Black Swan by Nassim Taleb. Now, the black swan is a metaphor for the unknown and the unexpected. I mean, in the old world, the theory was that all swans were white. So each instance of a white swan would make you think, yeah, that theory's pretty good. But the point is, you can never prove a theory true. And in fact, when people found Australia, they realized that there were black swans. What was interesting for me was that everyone I spoke to came up with a rule very early on and then only proposed numbers that fit with that rule they were thinking. I was looking for you guys to propose a set of numbers that didn't follow your rule and didn't follow my rule. I was looking for you guys not to try to confirm what you believe. You're always asking something where you expect the answer to be yes, right? Like you're trying to get at it. Yeah.
But instead you want to get the no.
You want to get the no because that's much more informational for you than the yes. Like if everything's giving a yes.
True. That is really true once you say that.
That is what's so important about the scientific method. We set out to disprove our theories. And it's when we can't disprove them that we say, this must be getting at something really true about our reality. So I think we should do that in all aspects of our lives. If you think that something is true, you should try as hard as you can to disprove it. Only then can you really get at the truth and not fool yourself.
Yeah, very good summary. So this YouTuber and Dorothy Bishop really inspiring in looking at some of these cognitive biases in research. This is the one that she used in her presentation. So the way that we do citations, and this is what she was trying to explain at the beginning, is that typically even for you, when perhaps you're doing your introduction, you're doing your literature review, you do a Google search and the first thing that comes in that supports what it is that you wanted to say, you use that and you put this in, but you haven't really done a systematic review of all of the literature. So we do all kinds of things like cherry picking, biased citations, and that's why we actually need literature reviews. So, we tend to trust citations that support our view. We cite supportive materials. We, read prior literature. To debias doesn't necessarily help. So it's a big question of how we should address this. One of the ways to do this is use a priori systematic objective criteria. Have other, just like in the UCLA professor, have other external experts to look at what you're doing. So next week, you'll have a bunch of experts coming in and looking at your Google Docs and trying to help you beyond the teaching assistants and myself looking at this, getting somebody who's objective, who's not invested in this research to really tell us if what we're doing is okay. Plus, we try to implement best we can the principles of open science. So whatever it is that we do, we try to explain from beginning to end what we did in order to allow everybody who wants to disconfirm what it is that we found to help us really get to the truth of things. Conclusion, and I think this is a very humbling experience as a researcher to understand that even after many, many years of doing research, and even after many years of teaching social psychology and judgment decision-making, and many projects and a lot of research and publications, we are still very much biased. Only 10% of researchers can answer a fundamental question about the way that we test hypotheses, and a lot of basic intuitions about even folding a newspaper or a chessboard can fool most of us. So being an expert doesn't necessarily mean that you know a lot more. We need to work more with students, with YouTubers, with the general public in order to work together to get to the truth and to science being accurate. So that wraps up the cognitive biases aspect. Hopefully this will be an interesting task for you, working on this with your team, looking at one of these cognitive biases. We'll put up a list and then you submit this. You have a chance to, of course, revise. That will be your third component, and hopefully we'll follow up on the steps of Dorothy Bishop to really help researchers understand the cognitive biases and how to overcome them. Okay, good. So we'll talk on Slack and I'll see you next week.